Hi, I'm Navdeep. I'm one of the instructors at SCALER, and today we are going to talk about a technique called prefix sum, which is used to solve problems on data structures and algorithms. So without further ado, let me share my screen and let's discuss this technique. So in this video, the content that we would be going through is first we would be talking about the problem on queries which inspired this solution or this technique called prefix sum. And we would be starting with its brute force solution. Then we would talk about the intuition behind the prefix sum solution. And then we'll talk about the prefix sum construction and the solution that the solution to the problem on queries that we started with. After that, in the end, we would be talking about a problem on prefix sum. So let's start with the video and let's start with the first problem which inspired prefix sum. In this problem, you are given n array elements and there are q queries on the same array. In those q query, in each query, you have to calculate sum of all the elements in the given range. The range is given by two elements L and R. You have to find sum of all the elements in this range. You are given that L and R would lie between 0 to n minus 1. So for example, if this is the query which is given to you, if this is the array which is given to you, and then there are three queries on this given array, let those three queries be 4, 8, which means that you have to find sum of all the elements starting from the 4th index till 8th index. So let me show you what is this query. This query says that you have to find sum of all the elements starting from the 4th index till 8th index. So sum of all the elements is going to be 5 plus 2 plus 8 plus minus 9 plus 3. So this is 7. 7 plus 8 is 15. 15 plus minus 9 is 6. And 6 plus 3 would be 9. So over here, the query 4, 8 would have an answer of 9. Then the next is 3, 7, which means you have to start from 3rd index and you have to find sum of all the elements till 7th index. So the answer to this query would be sum of all the elements involved in it. 4 plus 5, which would be 9, plus 2, which would be 11, plus 8, which would be 19, plus minus 9, which would be 10. So sum of all the elements in this query would be 10. Then the next element that we have is 1 to 3. The next query that we have is 1 to 3. And in this 1 to 3, we have to find sum of all the elements involved in this range. So the sum is going to be 6 plus 2 plus 4. And the answer to it would be 12. So answer to this query is 12. We have to answer each and every query. We have to find sum of elements in each query. Sum of all the elements involved in that range. So first, let's come up with any solution that comes to our mind. The best and the simplest solution that comes to our mind is of nested loops. The idea is that you query through each and every query. You go through each and every query. You find L, you find R, and you loop through L and R, and you find sum of all the elements that are involved in it. The simple code for this idea would be that you loop through all the queries. Obviously, before starting with this loop, you would have to take input of array elements and you would have to take input of Q. After that, you are going to loop through all the queries. In each query, first you are going to take input of L, then you are going to take input of R, then you are going to loop through all the elements starting from the Lth index and ending at Rth index, and you are going to sum all these elements. To sum, you have to take a variable and you have to assign it to 0 in the beginning, and then you have to do sum equal to sum plus array of j. After this loop is over, we can print the sum like this. This is the code for the brute force idea. The time complexity for this brute force idea, for this code, would be the iterations in this code are q, and the iterations in this loop would be R minus L plus 1. So the time complexity would be Q into R minus L plus 1. Over here, we have to take the worst case value of R and L. So what is the biggest value of R and L? So the biggest value of R and L would happen when L would be 0th index and R would be n minus 1th index. That would be the biggest range. So for each query, if I take the biggest range, then the time complexity would be Q into n minus 1 minus 0 plus 1, and this would be Q into n. So my time complexity in terms of big O notation would be Q into n. This time complexity is very bad. So we would have to optimize it further. But before talking about the optimization, first we have to understand the intuition behind the optimization. So let's go over this intuition. Over here, I have given you the Indian team score for the first 10 overs. Look closely how the scores are given. The scores are given in the form of total runs scored so far. So this is the keyword over here. Total runs scored so far. We have the over number, and after that over number, we have the total runs scored. So at the end of first over, the total runs scored were 2. Similarly, at the end of second over, the total runs scored were 8. And at the end of third over, the total runs scored were 14. So on and so forth, we have the total runs that are scored at the end of each over. Now, if somebody asked you these queries, what is the first query? The first query is, what is the total run scored in the last over? Then to answer that question, you would say that the total number of runs scored in the complete 10 overs is 97, and the runs which are scored in the first 9 overs are 88. You just have to find the runs which are scored in the final 10 over, final 10th over. So for that, what you will do, you will subtract 97 from the total runs which are scored in the first 9 overs, which is 88. So subtract 97 and 88 and you would get 9. So subtract the contribution of first 9 overs from the total number of runs scored in the 10 overs. So you have to do it like this. Now let's talk about what would be the total number of runs scored in the last 5 overs. By that I mean, what would be the total number of runs scored from 6 to 10 overs. Look closely, this is a range, and I would be solving the sum of all the elements in this range. So over here, what I would do is, I would say that give me sum of the total runs which are scored in the first 10 overs, and I'll subtract it from the sum or the total runs which are scored in the first 5 overs. And this will give me the amount of runs that are scored from 6th to the 10th over. How is it giving me? Because sum of first 10 or the total number of runs scored in the first 10 overs is giving me the total number of runs scored in 10th over, 9th over, 8th, 7th, 6th, 5th, 4th, 3rd, 2nd, and 1 over. It is giving me the total number of runs scored in these individual overs. And sum of first 5 overs is giving me sum of runs scored in these individual overs. If I subtract this part from this part, then this would get cancelled out and I would be left with only the runs which are scored in 10th over, 9th over, 8th, 7th, and 6th. Similarly, over here, when you are trying to find the total number of runs scored just in the 7th over, for that what you have to do is, you have to find total number of runs scored in the first 7 overs, and you have to subtract it from the total number of runs scored in the 6th over, till 6th over. till 6th over is what is stored over here, and till 7th over is what is stored over here. Okay. Similarly, if somebody asks you what are the total number of runs scored between 3 to 6 overs, then how are you going to solve this? You are going to say, find me the total number of runs scored at the end of 6 overs and subtract it from the total number of runs scored in the first 2 overs. So look carefully. Over here, I have answered a query. I have answered for a range, but I have answered it with the help of a formula. And this is the same formula, this is the same approach that we are going to apply to solve the previous question, right? So over here, what is the most important thing that you have to focus on? Over here, we are not focusing on each over's contribution. We are looking into total number of runs scored so far. We are looking into cumulative score. So in general, we have to look into cumulative information to come up with the answer to queries. So now let's get back to a question. Let's say this is the array which is given to us. Now for this array, let's create a cumulative information first. So tell me what are the total number of runs scored from 0th index till 0th index. Or what is the total sum of elements starting from the 0th index till 0th index? It would be -3. So let me write it over here that I'm converting this into its cumulative information. Just a second. This is information. What is the total sum so far? That is the question. So starting from the 0th index till 0th index, what is the total sum? It is -3. Starting from the 0th index till first index, what is the sum? It is -3 plus 6, and it would be 3. Now the total sum starting from the 0th index till the second index, what it would be? It would be 3 plus 2, it would be 5. Right? It would be -3 plus 6 plus 2, it would be 5. Similarly, the cumulative information starting from the 0th index till third index, what would be the sum? It would be 9 over here. Starting from the 0th index till 4th index, what would be the combined sum? It would come out as 14. Starting from the 0th index till 5th index, what would be the cumulative sum? It would be 16. Starting from the 0th index till 6th index, what is going to be the cumulative sum? Over here, it is going to be 24. I'm just writing the cumulative sum information. This would be 15. From 0 to 8th index, the cumulative sum information is going to be 18. And starting from 0th index till the 9th index, the total sum, the cumulative sum is going to be 90. You can do the calculations and you would find that this is exactly correct. Now somebody comes you with a range query and he asks you, find me sum of all the elements from 4th index till, let's suppose, 6th index, right? So they are asking, tell us what would be the sum of all the elements in this range, right? What would be the sum of all the elements, right? So if we do it manually, sum of all the elements is going to be 5 plus 2 plus 8. This is going to be 13 plus 2, it is going to be 15. But we do not have to do it manually. Let's try to solve it with the help of the cumulative sum information. So can I say that this would be equivalent to sum of all the elements starting from 0th index till 6th index, and from that subtract the contribution of sum of all the elements from 0 to 3rd index. You have to find sum of these indices, right? 4, 5th and 6th. So what we are going to do, we are going to find sum of all the elements from 0 to 6, and from that we have to subtract sum of all the elements from 0 to 3. Because if we subtract this, then these would get cancelled out and we would be left with sum of 4, 5th and 6th index only. So over here, what is sum of all the elements starting from 0 to 6th index? it is given to us as 24. And let's subtract sum of first three elements, not first three elements, first four elements. So we have to find sum of all the elements starting from the 0th index till 3rd index. So that is given to us as 9. We subtract 9 from 24 and we get 15. So we see that the answer is coming exactly correct. So that is the best part in this. You have come up with the answer and you did not have to traverse manually over all the elements in the range. That's the best part. Let's solve some more questions. For example, if somebody comes to you with another range, let's suppose they ask you that tell us what would be the sum of all the elements starting from the 1st index till 5th index. Then let's manually do it. So if we manually do it, sum of all the elements starting from the 1st index till the 5th index is 6 plus 2, 8, 8 plus 4, 12, 12 plus 5 would be 17, 17 plus 2 would be 19, and 19 plus 8 would be 27. So 27 is the sum that is coming to us. But with the help of the formula that we have created so far, we would say find sum of all the elements starting from 0 till 5th index, and from that subtract the sum of 0, 0. Just subtract the contribution of the first element, which is the 0th index element. So if we do that, sum of all the elements starting from 0 till 5th index is 16. And if we subtract sum of all the elements starting from the 0th index and ending at 0th index, we come out as -3. So if we add them, if we subtract them, this would come as 16 plus 3, which is going to be 19. This is not matching with this manual query that we have taken. So let us go over the manual query once again. So this is 6 plus 2, which is 8. 8 plus 4 is 14. 8 plus 4 is 12. 12 plus 5 would be 17. And 17 plus 2 would be 19. I think we added 8 incorrectly. We should not have added 8. So the answer from 1 to 5 is 19. And it is sum of 6 plus 2 plus 4 plus 5 plus 2. These are the 5 elements that we have. 6 plus 2, and this is 4 over here, right? So this comes out as 19. Sum of all the elements from the 1st index till 5th index is 19, and from our formula also it is coming out as correct. Now, one more thing that I wanted to ask you is that let's suppose somebody asks you what is the sum of all the elements from 0 till 5th index. For that, do you have to apply the formula? If somebody asks you what is sum of all the elements from 0 till 5th index, you can directly go and you can directly return 16. You can directly go and you can directly return 16, right? Similarly, if somebody asks you what is sum of all the elements starting from 0 till 7th index, then you can directly go and you can return 15. So I can say that let's generalize this part. If you have this cumulative information, let's suppose if you have this cumulative information, and then if somebody comes to you and somebody asks you what is sum of all the elements starting from the left index and ending at right index, then you can say that this would be sum of all the elements starting from the 0th index ending at the rth index if L is 0. If L is not 0, then this would be equivalent to sum of all the elements starting from the 0th index till rth index minus sum of all the elements starting from 0th index and ending at L minus 1th index. So just with the help of cumulative information, if you have this cumulative information already pre-processed, then you can answer any query with the help of this formula. You would not have to traverse over all the elements. You would not have to traverse over all the elements of the given range. And you can answer all the queries with the help of this formula. Now, the main focus that we have to do is we have to focus on constructing this cumulative information. How do we construct this cumulative information? So let's bring the same example that we had over here. So let me bring this example. And let's try to construct this cumulative information. And let's see what is the best that we can do with this cumulative information. So to construct this cumulative information, we have to see that in the beginning, you have to see this cumulative information stores the sum from 0 till the 0th index. So that is equivalent to the element which is stored at 0th index. Okay, so let's create a sum array. Let's create a sum array, right? Over here, if I say that sum of 5, this would mean sum of 0, 5, starting from the 0th index and ending at 5th index. Or let's give it a better name. So let's give it as prefix sum. So prefix sum of 5 means sum of all the elements starting from the 0th index and ending at 5th index. Okay. So over here, you know that prefix sum of 0 is equivalent to sum of all the elements starting from the 0th index and ending also at the 0th index. That is equivalent to array of 0. So in the beginning, I'll write -3 over here. Then let's try to answer for other queries. So what is p sum of 0? P sum of 0 is array of 0. Now let's say what is p sum of 1? What is p sum of 1? It would be equivalent to sum of 0, 1. Can I write this as, this would be sum of 0, 0 plus array of 1. We can write this, right? So this would become prefix sum of 0 plus array of 1. This would become 6 plus -3, and the answer would become 3. Similarly, let's talk about the next index, which is p sum of 2. What is p sum of 2? It is sum of all the elements starting from the 0th index and ending at 2nd index. We can also write this as sum of all the elements starting from the 0th index, ending at 1st index, and we just need to add the 2nd index at the end. So this would become, I can write this as prefix sum of 1st index plus array of 2nd index. So this is just the sum of these two elements. So previous value and the recent value, the current value of the element that we are looking at, this would become 5. Now similarly, if we have to find p sum of 3, this is going to be p sum of 2nd index, which contains sum of all the elements starting from the 0th index and ending at 2nd index, plus the current element, which is 4. So it is going to be 5 plus 4, it is going to be 9. Similarly, let's calculate p sum of 4. Let's calculate p sum of 4. This can be written as sum of 0, 4, which can be written as sum of all the elements starting from 0 and ending at 3rd index, and just add the last element, array of 4, to it. So this would become p sum of 3, and we just need to add array of 4 to it. So this would become 9 plus 5, this would become 14. So I can say that if you have to calculate p sum of ith index, then you have to say that this is equivalent to p sum of I minus 1 plus array of I, the current value, right? So I can say this would become 14 plus 2, this would become 16, and you do 16 plus 8, this would become 24. You do 24 plus -9, this would become 15. You do 15 plus 3, this will become 18. And you do 18 plus 1, this would become 19. So this is how you have to find the cumulative information. This is the generic formula for finding cumulative information. And in the beginning, you have to start by mentioning p sum of 0 is equal to array of 0. So if I write the pseudocode for finding or for constructing a prefix sum, it would be, if you are given an array of size n, if this is given to you, then a prefix sum would also be of the same size, n. And then I'm going to say that prefix sum, let's create the nomenclature. Let's keep the nomenclature same. So let me write, this is p sum of size n. And in the beginning, I would say p sum of 0 is equivalent to array of 0. Okay. And then we are going to construct with the help of a loop. So I'm going to start from the first index. I'm going to go all the way up till n-1 index, and let's do I++ over here. The value p sum of I is going to be equivalent to p sum of I-1 plus array of I. The same generic formula that we created in the last example, right? So this is how we construct it. And the construction over here takes n iterations to complete. Okay. So this is how prefix sum is constructed. And now let's combine the construction and the generic formula that we created to solve all the queries. And now let's try to solve the original question, and then we will try to find the complexity, how much we have reduced the complexity, how much optimization we have been able to get. Okay, so let's move a little bit down and let's create the sum of queries question over here. So first, let me bring the construction pseudocode over here. So the construction pseudocode is going to be something like this. Let me copy it and now let me paste it over here. Okay. So something like this. Yeah. So we have constructed. After this construction is done, now you have to answer all the queries. How do you answer all the queries? So let's come up with that part as well. So now you are given Q queries. So obviously you would have to take input of Q, and then we would be running the loop through each query, less than equal to Q, and I would say I++ over here. Then I would take input of L over here, and I would take input of L over here. Then I would simply ask that if L is double equal to 0, my answer would be print sum of, or rather than keeping it this way, the name is p sum. It would be p sum of R. Because L is 0, this means that this is 0, R. What is sum of 0, R? Sum of 0, R is stored in p sum of R. That's why if L is 0, we directly need to go at p sum of R and we need to return that result. Okay, so yeah. Else, if L is not equal to 0, then my answer would be print p sum of R and subtract p sum of L-1 from it. So this is how this sum of query question now looks like. Let's try to find the complexity. Over here, the complexity for this question looks like, for the construction part, I think there are n iterations involved in it. There are n-1 iterations because we're starting from the first index and ending at the nth index. But we can take approximations and we can say that there are n iterations over here. Similarly, I can see there are q iterations over here. We do not have a nested loop now. We only have a single loop. So the time complexity would be order of big O of Q plus N. This is a definite increment or optimization or improvement over the last time's time complexity, which was Q into N. We have come from Q into N to Q plus N. Just because we are seeing the given information in the form of cumulative information, and with the help of these cumulative information, we are answering each and every query, right? This is how magical it is. This is how you can improve the time complexity from Q into N till to Q plus N. Now, since you have understood this part, one more thing that I want to bring into your consideration is the space complexity part. To improve time complexity, you have taken extra space complexity. Let's go to the original brute force solution that we had. So in the original brute force solution, the space complexity, what was the space complexity? You are having only few extra variables. One extra variable was I, and there was another extra variable called j, and there was an extra variable called sum. There were 3 extra variables that you were taking. So the space complexity was 3 into 4 bytes because one integer takes 4 bytes. So it was independent of input. The space complexity was independent of input size. So I would say the space complexity was constant. But over here, when we had the optimization code, over here we had the extra space. So the extra space is for the prefix sum. Extra space is of order n. So space complexity is order n over here. Space complexity is order n over here because you are creating an array of size n, exactly of the same size as the given array. So this is one thing that we are sacrificing. We are taking extra space to bring down the time complexity. Okay, our space complexity has increased, but our time complexity has decreased. So now, since you have understood this part, now I want to bring your attention, or I want to solve a question on prefix sum. Let's apply our knowledge that we have gained so far onto a question. The name of the question is equilibrium index. It's a famous interview question. It is asked many times in many interviews. So the question is that you are given n array elements. We have to count number of equilibrium index. An index is said to be in equilibrium if sum of all the elements before the ith index is equivalent to sum of all the elements after the ith index. Okay. So over here, what we have to do is we have to check how many equilibrium indexes are there. Okay. So this is the main definition that you have to keep in mind. The definition is that ith index, for the ith index, you have to check whether sum of all the elements from the 0th index till I minus 1th index is it same as sum of all the elements from I plus 1 till n minus 1. So this needs to be n. So the left side elements and the right side elements, if the sum of all these elements is exactly same, then I would say I is an equilibrium. There are 2 noteworthy exceptions. When we are standing at I equal to 0, at that point of time, there are no elements on our left hand side. So we have to take sum of left side elements as 0. And when we are standing at the last index, which is n minus 1, then there are no right elements. So we have to take sum of right elements to 0. So these are the 2 things that we have. Now let's try to solve this question with the help of examples. Try and solve as many examples as possible, and you would be able to see that algorithm is coming in front of you. You are able to trace that algorithm. You are able to get the optimized solution. So try to solve as many examples as possible. Now let's try to solve the first example. The first example that we are doing over here is just to understand what is the question given to us. So this is the first index. let's check whether this is an equilibrium index or not. For it, the left sum and right sum. Try to find its left sum and right sum. Left sum is 0 because there are no elements to its left hand side. There are no elements to its left hand side. For it, the right hand side contains these three elements, 2, 4, and -1. So the sum is 6 plus -1, which is 5. So the sum is going to be 5. So obviously, 0th index is not equilibrium index because left sum and right sum are not same. Now let's talk about this element. For this, the left sum is going to be -3. What is going to be the right sum? The right sum is going to be sum of 4 plus -1, which is 3. So this is also not an equilibrium index. Now let's talk about this element. If I look into this element, the sum of left side elements is -3 plus 2, which is -1. And sum of right side elements is -1. So both the sums are same. So that's why this is an equilibrium index. So let's mark it some way. Let's mark it this way. Okay, let's check for the last element as well. For this, the right sum is going to be 0 and the left sum is going to be -3 plus 2 plus 4. It is 6 plus -3. It is going to be 3. So this is also not an equilibrium index. There is only one equilibrium index, which is the index 2. So the count is going to be 1. The answer should be 1. Okay. Let's look into 2 more examples and then we would be able to understand this problem really well. I hope you have understood the problem, but now we are going to talk about coming up with the solution also. How do we solve this problem? Right? Okay. So over here, in this example, you will go over each and every index. The first index. For the first index, what is the left sum? The left sum is 0. And what is the right sum? The right sum is sum of all these elements. 1 plus 5 is 6, 6 plus 2 is 8, 8 plus -4 would be 4, 4 plus 3 would be 7, and 7 plus 0 would be 7. So over here, the answer is going to be 7. So this is not an equilibrium index. Talk about first index. So the left sum is -7. The right sum is going to be 5 plus 2, 7, 7 plus -4, it is going to be 3, and 3 plus 3, it is going to be 6. So left sum is 6. Sorry, right sum is 6. So this is also not an equilibrium index. If I talk about the next part, the second index, left sum is -7 plus 1, which is -6. Right sum is 2 plus -4, which is -2. -2 plus 3 is 1. So this is also not an equilibrium index. Let's talk about the next element, which is the third index. Do the right sum and do the left sum. What is left sum? Left sum is -7 plus 1, which is -6. -6 plus 5 would be -1. And the right sum is -4 plus 3, which is -1, plus 0, which would also be -1. So this comes out as equilibrium index, and let us mark it with the green pen. Let's talk about the next index, which is the fourth index. What is the right sum and what is the left sum? Left sum is -7 plus 1, which is -6. -6 plus 5 is -1, and -1 plus 2 is 1. And on the right hand side, the sum would be 3 plus 0, which is 3. So this is not an equilibrium index. Similarly, if I talk about this part, this is coming out as the fifth index. And for this fifth index, what is going to be the left sum? The left sum is going to be -7 plus 1 -6. -6 plus 5 is -1. -1 plus 2 would be 1. 1 plus -4 is going to be -3. And the right sum is 0. So this is also not an equilibrium index. And let's talk about this part. Let's talk about the last index. For the last index, what we are going to do is we are going to find the left sum. The left sum is sum of all these elements, which is 0. Sum of all these elements is 0. You add all these elements, you would get 0. And the right sum for the last index is also 0. So I can say this is also an equilibrium index. This is also an equilibrium index. So for this example, the count of equilibrium index are 2, right? So the simple approach that comes to my mind is that we can loop through each and every index and we can try and check whether it's an equilibrium index or not. We can find some of the elements on the left hand side and we can find some of all the elements on right hand side, right? This is one other example that we have. Let's quickly try to answer this question. And let's quickly write the left sum over here and let's quickly write the right sum over here. So this is the 0th index. For it, the left sum is going to be 0 and the right sum is going to be minus 2 plus 2, that is also 0. So this is an equilibrium index. Then let's talk about the first index. For the first index, sum of all the elements on the left hand side is 3, sum of all the elements on the right hand side is 2, so it's not an equilibrium index. For the last index, which is the second index, sum of elements on the left hand side is 3 plus minus 2, which is 1. And sum of elements on the right hand side is 0 because there are no elements on the right hand side. So this is also not an equilibrium index. So I have only one equilibrium index over here, right? So my answer is going to be 1 for this question. Now let's talk about the pseudocode. So the idea is very simple. The idea is loop through each and every index and find sum of elements on the left hand side and sum of elements on the right hand side. If the sum of both these elements sum comes out as same, then we can say that it's an equilibrium index and we can increase the counter, right? After coming out of the loop, I can say that the counter would be my answer. So let's apply this simple idea. We are given this array as our input. Okay, so we'll keep a counter over here and we'll loop through all the indices I equal to 0 and I equal to n minus 1. Starting from I equal to 0, we'll go through each and every element till I equal to n minus 1. So we are looping through each and every element. So let's start with this. For each I want to find sum of all the elements on his left hand side. So we need to find sum of 0 to I minus 1. Sum of all the elements from 0 to I minus 1. And similarly, we want to find sum of all the elements on the right side, which is sum of all the elements from I plus 1 till n minus 1. Simple, easy peasy, right? And if these sums are equivalent, so let me bring it a little up. So if these elements are same, then I can increment my counter. So let's say that we mark the first sum as L sum and we mark the second sum as R sum. So if R sum and L sum are same, then I can increment my counter as C equal to C plus 1. And after coming out of this loop, I can print or I can return this counter C. Let me print it. So I can print the value of C. This value C is going to be the count of equilibrium indexes. Okay. So this is the part. Now, one way to solve this is you can loop from 0 to I minus 1 and you can loop from I plus 1 to n minus 1. But there would be no fun in it because we have just learned prefix sum. And this looks like a range. Whenever we see a range, we can solve it using prefix sum. So that is exactly what you have to do over here. So let us try to solve it using prefix sum. So can I say that these are two ranges that are given to me and both of these ranges can be answered using prefix sum. But before going into the prefix sum, we have to construct prefix sum. So let's say P sum is the array that we have to construct. So construct P sum. That is the part that you have to work upon. This I'm leaving as an exercise because I've already done this part. So you can bring the same code over here or you can write the same code over here and you will be able to construct the P sum. Now, once the P sum is constructed, then you can find some of these ranges. What would be the L sum? L sum over here would become P sum of I minus 1. P sum of I minus 1. And similarly, what would be R sum? R sum would become P sum of N minus 1 minus P sum of I. I've done nothing. I've simply applied the formula. I've simply applied the formula that we had earlier brought up. So this looks like the code. This looks like the code, and this is perfectly all right, but there are some edge cases, there are some corner cases where it will not work. Let's check for those corner cases. One corner case that I can directly see is when I is 0. When I is 0, I'm trying to find P sum of I minus 1. P sum of I minus 1. If I is 0, P sum of I minus 1 would give me P sum of minus 1, which is beyond the bounds, which is an incorrect index. If you are writing this code in Java or Python, it will give you index out of bound error. Okay. If you're writing it in C++, then it will give you an incorrect answer. Okay. So for doing that part, what I can do is, I can do a small thing. I know when I is equal to 0, for that left sum is always equivalent to 0. Left sum is always equivalent to 0 because there are no elements on the left hand side for I equal to 0. So in the beginning, let's say we are taking left sum equal to 0. Then what I can say is that only calculate this value if I is greater than 0. So if I is greater than 0, then only you should calculate this value. Otherwise, you should not calculate this value. For I equal to 0, left sum is already given as 0. If I is greater than 0, then we will calculate it using this formula. Right? For I equal to 0, left side has been handled. Now let's talk about the right side. So if I is equal to 0, my right sum would become P sum of N minus 1 subtracted by P sum of 0, which looks fine. There is no error in this code and there is no error in this equation. So it will work perfectly fine. The right sum would work perfectly fine for I equal to 0. Let's now try to find for I equal to N minus 1. For I equal to N minus 1, what you can see is that for I equal to N minus 1, my left sum is going to be P sum of N minus 2, which is perfectly fine. What is my right sum? My right sum is going to be P sum of N minus 1 minus P sum of I, which is N minus 1. P sum of N minus 1 subtracted by P sum of N minus 1, these two are going to cancel out each other and the answer is going to be 0. Okay. So my right sum is also catered. For the last index, right sum is 0 because there are no elements to its right side. So there is no need of handling it for I equal to N minus 1. The only index that we had to handle was I equal to 0. Only the left part of I equal to 0 was to be handled and we have handled it. So now this code will work perfectly. The only thing that I want to improve is this N. Let's be uniform and let's use the same symbol of N in all the pseudocode. And in everywhere I had used the small n. So over here also, let me use small n. Okay. Now this is the pseudocode. What would be the time complexity? So for time complexity, I can see that the number of iterations in this loop are n. And inside this loop, there are no more nested loops. So I can say the total number of iterations are n. And the time complexity would also be big of n. Space complexity, if I talk about space complexity, then space complexity comes out as order of n because we are using an extra array of size n to answer this question, which is the prefix sum array, right? So in this way, you can answer this question called equilibrium index called count of equilibrium index. I hope with the help of this pseudocode, you will be able to code this in your favorite programming language. And I also hope that you have understood what is prefix sum and you have applied the concept of prefix sum in one question as well. Going forward, we will be solving more questions of prefix sum in other videos. But for now, this was all that I wanted to explain on prefix sum. Thank you.